Good morning, everyone. Today is July 25th, 2020, and this is the John Chappell Natural Philosophy Society Science Chat. And looks like we just got you here today, Bob. So maybe we'll discuss Weber electrodynamics.
Yeah, if you'd like. I have a paper which I'd like to point out to you and everybody, either now or
We've got
later.
two people on the live stream now. Hello, everyone. Okay.
Yeah.
Yeah, so go ahead, Bob.
Well, I'm trying to. Let's see. Alrighty. Share my screen. Click share screen. Share screen. Share entire screen. Okay. Can you see my screen?
Okay, I'm going to add the screen there. There you go. Yeah, we got that.
So this paper, accurately predicting electron beam deflections in fringing fields of a solenoid. And what this research group out of Liverpool, I believe, did was to look at 3 different models for predicting the behavior of an electron beam as it passes by a solenoid. I can show you the setup here. Here's a, let me know if you can see this, a solenoid over on the right, and what they have is an electron beam passing by the solenoid. And a little better picture to that is this one. Again, they got the solenoid. They have an electron gun shooting out beams past the solenoid, and then a fluorescent screen where they can see where that beam hits the screen, you know, how that beam is deflected. And so they looked at 3 different models. One is Weber's force equation, which is highlighted here. Sorry. The model we present follows direct approach laid out by Weber, blah, blah, blah. Weber's force equation given here. The other model that they are comparing against is the usual Maxwell Heaviside, the Lorentz force equation. This one here. And then there's some software which they're using for modeling, which has its own force equation built in. I don't know what that is. They say here some state-of-the-art commercially available software. So they're comparing those 3 and looking at the data. For example, here, the blue is the experimental data. The red X is Weber. The triangles is the field that's the Maxwell-Lorentz force equation, and then CPO is the software. And if you look, red X and blue squares, it's pretty close. That's the Weber prediction is pretty close to the experimental data. And yet the Lorentz force equation, these orange or yellowish triangles, is way off for this particular experiment. And then they do it with other solenoids. And so anyway, their conclusion is, in part, the deflection of an electron beam across 3 different size solenoids has been tested experimentally and was predicted with 3 distinct models. One is a field model based on the equations of Maxwell and Lorentz. The second is a field-based numerical model from a commercial software package, which utilizes the boundary element method. And the third is a direct action at a distance theory based on Weber force. It was found that in general, for the limiting condition that the velocity is much less than this of the electron beam, it's much less than that of the speed of light, that is in the low velocity regime, the experimental data has good agreement with the Weber based model. So here is, again, experimental data, which shows that in this low velocity regime, the experimental data is well predicted by the Weber base model, which to me is that's really encouraging. Of course, you guys here know that I'm a big Weber fan and been pushing Weber electrodynamics here. But I will say that I am well aware that Weber does not fit all experimental data everywhere and at all times. But it is much better than the Maxwell-Lorentz force equation in the low velocity regime. And this is experimental data showing that. So just wanted to point that out to everybody here. And it's a pretty good paper. I've put a link to it in the chat, at least the private chat. Let me see, stop sharing. And just wanted to bring it to people's attentions today. Thanks, Franklin.
That's very interesting. I mean, I find it especially interesting that basically the Lorentz force law is not confirmed. That would be a very basic disproof of something that is commonly accepted. I mean, it might be like it's like close, it's not like it's like totally off or anything like that. But it could clearly be a lot better.
Right? Yeah, the Weber stuff is better. It beats out that Lorentz force equation. But again, in the low speed, you do experiments at high speeds, close to the speed of light, and Weber force equation fails, and it's the Lorentz force law, which seems to be correct with the special theory of relativity corrections, the gamma factor and all that stuff. That seems to then be a better fit to the experimental data than the Weber stuff. So, it kind of depends on what regime you're talking about. And my question is, why can't we get one equation that works everywhere? I don't get it.
Well, did the paper also do experiments with variable speed? Because they seem to be indicating that, there is this difference. But did they do, I don't know if you can get electrons to go at the speed of light per se, but did they then repeat those experiments and show that that Lorentz force was more accurate at those speeds, or where did they get that from?
Yeah, they mention it and they give references to other papers, but here is where I'm not going to try and speak for the authors. I don't know exactly. I do recall them, referencing other papers when they were talking about speeds close to the speed of light. And so I don't know what those experiments were and how those experiments were set up and whether they, were involved or if it was just a different research group that they were referencing.
Yeah, that's always kind of a problem when they make some kind of statement like that and they're referring to some other paper. But now, basically, so Weber the electrodynamics formula that would start with by analyzing the currents in the wires, right? As opposed to seeing out the Lorentz force law. That's already presuming what the magnitude of the magnetic field is, right? And how could you do that without, I don't know, either directly measuring it or you'd have to do what Weber is doing, which is to calculate it based on the speed of the electrons in the solenoid kind of thing, right?
Right. The Weber starts with just two charged bodies. And from that, you do a lot of algebra and more algebra, and you come up with the force of a current loop in a solenoid on an electron. And I don't know.
Is that in order to use the Lorentz force law, you have to come up with an actual pre-existing magnetic field. Lorentz
Right.
force law doesn't presume that it's being caused
Right.
by, I don't know, anything. It's just kind of out there, right?
Right. That's a
So
big complaint. That's a big complaint of the Lorentz force equation, at least my understanding of it, is that in the Maxwell electrodynamics world, you don't derive that equation, that force equation. It just kind of gets added in. Whereas Weber, you start with something simple and you derive the force equation. The Maxwell stuff, it's, well, here's the force equation to use. Yeah, but under what conditions? Can you use that Lorentz force law for the force on one charged body on another charged body? Or is it only restricted to the force on an electron due to some current in some wire? Well, what if you don't have a wire? What if it's a plasma? Can you still use the Lorentz force law? Those kind of questions don't seem to be answered in the textbooks, at least not satisfactory to me. They just say, here's the force law.
Well, I can kind of see that that's applicable. Like we have the magnetic field of, say, the Earth, and we don't know where's the wire, where's the current for that thing. But yet, using Lorentz force law, we can calculate if I shine an electron beam, it's going to be deflected by so much due to that presence of that magnetic force, which you measure with like a compass or something. There's ways. Measuring the magnetic field to that precision is kind of like, well, how do you do that, right?
Yeah.
It's one of those things where we have these equations and we believe them to be true, but to a certain extent, like I may not believe it. Like one of the things I was looking at is like the say the conservation of momentum law, which says that if I have two spinning objects and I reduce the distance by half, the speed will actually quadruple, right? Which is hard to believe. And I did, and so I had to actually perform an actual experiment to see whether it actually happened.
Cool. Did it?
Well, actually, it did. It was very difficult to design an experiment that reduces the friction when you have build a mechanism that has two weights, and then you can reduce the radius. And when you reduce the radius, you don't introduce additional friction or anything like that. It's very difficult. And indeed, I mean, my first attempt showed that it wasn't conserved. It's like, no, it doesn't look like it's conserved. But as my experiments got more sophisticated, then I was able to at least confirm to myself that that sort of thing happens here. Well, let's see. It looks like we got a few other people here today. We have James here, and we also have Alistair.
Hi, James. Hi, Alistair.
Let's see here. Let's see. Add to stream. Here we go. Here we go.
Yo, how's everybody?
Good. Oh, looks like
Great.
we got your ether particle there as your icon now, right?
Yes, and I've learned more about it too. I've been on a sabbatical for 4 months, government enforced sabbatical.
Having to do with COVID?
Pardon?
Having to do with COVID? Or that was
No,
just
I've learned a lot having to do with physics.
Well, what new things have you learned about your particle then? What's news?
As well as it being a combination of an E mode wave and a B mode wave to arrive at that shape is also a gravity wave with 1/4 wavelength, 1/4 of the radius of the sphere, then mapped across the surface of the sphere. So you end up with the wavelength mapped onto the hemispheres, 2 cycles on one hemisphere that is expanding, and then 2 cycles that are off phase to it, expanding in the opposite direction. And then on the lower 2 hemispheres, you see those same 2 gravity waves again mapped onto 2 hemispheres that are then collapsing. So what you have is a expanding and collapsing gravity wave mapped onto a sphere, which when you then stack it into the hexagonal stacking pattern and give it motion, results into patterns that makes the quarks that make up the neutrons and protons. And all along we've been looking for, why is there a 1 to 137th ratio between the electron and the proton? And I can now answer that question because of the geometry and then the quantity. So when you have 1 in the middle and then you expand it to 12, and then you expand again, add another layer and another layer, and then you rotate them and create the cuboctahedrons in the middle, it's like you make 3 sets. One that has a black ball in the middle where there is none in the middle of its 12, because the 12, if they're in the right synchronicity, can act as though one is in the middle even when one isn't there. Because they're ridges, they can propel against each other as though one is in the middle, and even if it is or isn't, doesn't matter. So basically you get a cuboctahedron with, on one side of it, a black ball, and on the other side of it, a white ball, representing the density from the set. Oh shit, I kind of didn't explain that good, but anyways,
Yeah, you kind of lost me.
it's better when I showed the one picture that shows the cuboctahedron. Well, anyways, the point is, I found that there is already an established known cuboctahedral nature to the quarks. When you look at a picture, some pictures of quarks, it's very obvious that they have a cuboctahedral nature. And so
well, let's try and explore that, because I don't know that. I mean, other than showing quarks as like 3 little balls and a proton, I don't know that.
I think his name is Eugene something, does a lot of YouTube videos, and one of his YouTube videos shows them. I can upload the image from it, or do you want me to take over the screen for a minute?
Yeah, you can share screen if you've got some pictures.
Okay.
I mean, I kind of got, it sounded like you made some progress, but really I'm kind of lost almost from the start there. You mentioned things like gravity waves.
Okay, well, that's primary. That shape is a gravity wave times a few cycles, 4 plus a sphere put together. That's what that shape is. That's where it came from. It was published in.
See, that whole statement doesn't make any sense. So, a gravity wave with a quarter wave of a sphere.
It was published in 2001 in Scientific American. I didn't know it was published so long ago, that specific shape.
Yeah, you got that from the Scientific American, but I don't know that any of those terms can be used like that.
I know the actual equation of the sphere, of the ball. The psi and epsilon and all that crap. I have that.
Why don't you go ahead and share your screen, and we'll see if this makes any more sense.
Okay. So what do I do?
On the bottom of your screen, there should be a control that says share screen, and you click on that.
Oh yeah, share screen, got it.
It'll give you some warning, and you click OK on that. Now, hopefully you're not on Chrome, and it's not going to kill you.
Oh, I am on Chrome.
Well, you can try it, but it might take you out. So if your browser closes suddenly, that means you can't do it, and you'll have to log back in.
I have the thing downloaded, the app. Like how I'm pretty sure it's a downloaded app as opposed to using Chrome natively.
You can go ahead and try it. It'll either crack on you or it won't. Okay, looks like I got something here. No, let's see. Yeah, Alistair's laptop. I got your screen here. So there we go. So there we go. We've got the infinity mirror effect here. So now you can go show us something else on your screen. There you go.
Okay, are you seeing the whole Google window?
Yeah, we're seeing the whole Google window.
Wait, that's not what I wanted anyways here.
You want to see the cool infinity window.
Yeah. Wonder what the heck's causing that.
It's just a
Okay.
mirror effect.
So now you're seeing my image editor, right?
Yes, we see that.
Don't need that one. Don't need that. That's just showing one when it's in motion to show that it becomes bigger than a single one would be because it's constantly kind of hitting in places where it wouldn't hit if it wasn't at that same angle. And that, you know what I mean?
It's just like vibrating, you know, rotating perhaps.
That's it rotating. I kind of just kept on copying it and overlaying itself a bunch of times just to show that when it's in motion, it gets virtually bigger. It creates a part around the outside, which is sometimes there, sometimes not there.
Yeah, I get
Right?
that.
That's just common sense. Like when you spin a drill bit, it becomes to look like it's a solid column, but you know that it's half there, half not there. So yeah, what was I going to show? So see this little guy here?
Yeah, little stick figure guy. Yes.
Okay, so just imagine as he walks. So he's going to be going like up a hill, down a hill, up a hill, down a hill, etc. Then imagine if instead of the stick figure guy, you use this, right?
What is that? Looks like just inverted cones.
It's Einstein's light cone. It shows basically like 4 dimensions fragmented by the square root of 1 and the square root of -1 is showing there, right?
I don't know what that is, actually, honestly. So
Well, I'll show you later, but for now, just imagine it shows like orientation. So if you were like imagining it points straight down at the center of the earth, we're imagining this is like a little planet, right? So imagine if across the point was the guy's feet. So this is him above the earth. This is the level of him. So as he's going up and down the hills, this is going like this, right?
sure, yeah.
And as he walks this way, you can see gradually he's going from being in a valley to being in a plain that's in between the mountains and the valleys. So his level has come like not just left or right, but also towards us and away from us. You see what I mean?
So the point being,
so as he's walking across the hills, he's going like this quite rapidly.
yeah.
Okay. But as he's walking through the valley, it will seem to him as though he's like just walking along the bottom of a level valley, but he's actually gaining altitude because he's coming towards the plain.
Yeah, you have this smooth spot in the that runs
Right.
along the pole, from pole to pole.
Right. So if you were looking at elevations, this red peak is Mount Everest, and the deepest blue trench is Marianas Trench. And these are like the where we grow the wheat and shit. Right?
Yeah, that's at some intermediary level there, right?
Yeah. So as we come in this way, we're actually slightly doing. Sorry, I got to do a special function here. I don't know if it'll work. Oh, crap. Control Shift Z. Got it.
So
Okay.
far you're just kind of describing, you know, if the Earth was the size of this particle, what
Right.
how you would.
I'm trying to impart the complete awareness of the impact of the ribs. So they are the mathematics of what we have accepted as being called a gravity wave. I can show you one.
See, that I don't understand. I mean, I understand everything about, what you're describing with the
Okay.
surface here, but that has nothing to do with gravity or waves or anything that like they're trying to detect at LIGO or anything like that. So what's the relation?
Fair question. So let's just confirm that I knew what I was talking about when I said that. Hope there's nothing embarrassing in here. What do I need? Something about. Does that look like it's from the past? No, I don't think this is it. Blah, 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 blah.
This is an article about gravitational wave detectors.
Yeah, it was it's not what I was looking for. I have an article that's from like 2001. And it's Scientific American, but it's in the archive, so it doesn't say Scientific American. There it is. Sci-Hub Echo. There we go. So this is 2001 when it got printed, and it had a different story and it has a different description. And I didn't know about this until like just a few weeks ago. And also, I've interacted with one of the two authors of this and learned more about it. So there, here, the figure here shows the effects of a gravitational wave traveling from pole to pole with a wavelength that is 1/4 the radius of the sphere. Pretty dang exact. Divide the radius of the sphere by 4, slap a gravity wave across, made the shape. Now, the when they conceived the shape originally, when the guy responded to me, he says his choice of 4 was arbitrary because it was visually worked well. But when you think about it, I mean, it's just an integer number. Oh, that's not going to be the right one. I don't remember the guy's name now.
So let's get back to that. So you've got that picture, and he was saying that. Can you explain that again? Because I'm still kind of lost. So you get a gravity wave. So a gravity wave hits a sphere,
right?
And then the sphere responds in this manner here, right? That's what's going on here?
Look across these ones here. You got a regular sphere. When you hit it, it gets taller or wider. Like it's like making it oblong in the up, down, left, right, up, down, left, right, and then plastering them all at once onto one sphere. So it's like the heart beats twice, and boom, you plaster that down onto here, and it makes this. It's like the harmonic balance point between this and this, and this and this.
So it's like you take a sphere and you hit it with something. I don't know, like you could hit it with a BB or something, and it would pulse. So that's what it has to do with gravity waves then.
Yes.
Well, it does not necessarily have to do with, it's just a force. You apply a force to a sphere, and you can get that kind of wave reaction. That's how I would interpret it. But it doesn't necessarily have anything to do with, say, gravity or gravity waves. It's more about the physics of how a sphere performs when under stress.
Well, you understand that's a gravity wave, right? A bipolar
wave. A kind of gravity wave.
Bipolar radial wave. Yes. Okay. But there's also the other kind, the kind that looks like it's traveling down a tube. Easiest way to find that is by using GIFs because it shows up more there. There we go. This is what we detect when we're using LIGO and stuff. We're detecting this. You'll see it does like this kind of clockwise wormy thing.
That thing that thing, that's
Gravity wave. There you go. That.
How is that a gravity wave?
Like this. Like it's like a straight at your pulse. Like that.
Well, the wave, anything with a wave has to do with a varying intensity, I would say. Right. So if I got a gigantic lead ball and I put it closer to you and then I took it away, then technically that should create a gravity wave, right? So because the gravity strength is getting stronger and then it's getting weaker. And if it repeats itself, then you kind of got a repeating wave. So that's what a gravity wave is. So, but what does that have to do with your work? And I mean, because we know that your ball here, certainly other people have come up with it, but they're not claiming that that makes up, all the particles of the universe.
Nope, I know they ain't. I'm just explaining now that I know there's a tie-in to the mathematics of what else we're looking for called the gravity wave, and that tie-in is just this. It's like, see, if you imagine, like, see, the blue is like the tall and skinny. See, because it's skinnier here, just as tall there. And the red is like the fat and short. And the purple is like the in between.
Yeah, but here that's literally wave height. I mean, that's
right.
So that's
amplitude.
Yeah, it's well, as you were explaining before, if a little person was sitting on top of the surface of this thing, there are clearly hills and valleys and flat areas and such.
Right. But one of the things I was trying to point out is that he's not just going forward, backwards, backwards. Even this way, he is slightly like leaning forward on his surfboard and slightly leaning back on it. So this is not like, I was just trying to explain that we are looking for an explanation which includes the light cone. So when you say Einstein space-time light cone, okay, so that's this. And it ties into like, why are there 4 dimensions instead of 3 dimensions? It's because
what exactly is this light cone thing trying to show anyways?
The relationship between space and time when they expand and dilate and shit.
So they've got time, they have a fast light cone, they have a future light cone, they have
and so the question is, why is there this? And what I'm suggesting is, well, it's related to the fact that there's a difference in frequency and amplitude if you followed a path along here versus if you went doompa 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 doomp versus if you were going around. All of those produce different patterns, different frequencies and wavelengths and amplitudes. And because of that, this is like the middle space.
I'm still trying to understand what that really means. I mean, because that makes no sense to me at all.
If this was the purple flat plane mapped onto the sphere of the Earth, and this was the little guy standing up, This is his head smacking on the railings because of the boat rocking back and forth.
No, that doesn't make. I'm just, like I said, I'm just not getting what this whole light cone thing is doing.
Okay, sometimes they show it other way. Just give me a second. If you see it like with a bunch of layers.
Light is something that comes out of, say, a light bulb, and the only cone kind of thing I could see is if you were projecting it like a movie theater and the light forms a cone. That's the only kind of cone
No, it's
I
not
can
like,
think of.
it's not like shining light out of a flashlight. It's like the relationship between time and space and the speed of light and the frequency and the amplitude of the light.
See, I might have a problem with like all of that. This relationship between space and time. And I don't think there is any relationship between space and time per se, and I certainly don't believe in space time. Is this all based on space time stuff?
Well, okay, some stuff.
That's just me. So that's why I'm having a hard time understanding what this has to do with anything.
Okay, some stuff in physics is mathematically. I don't know what's causing this and how to get rid of it.
No, it's a feature, not a bug. So you just have to put anything else in front of your screen.
Okay, there we go. Some
There you
things
go.
in physics we have established are mathematically extremely close to representing reality, if not exactly representing it. One of those things is a kind of duality or split personality to existence, right? A fourth dimension sort of thingy.
Yeah, but fourth dimensions don't exist. You can calculate them. You can have a fourth dimensional cube and it has a fourth dimensional volume, but doesn't mean anything. That's why I kind of have a problem with scientists who make calculations like that, completely divorced from reality. But now you're saying that you've this is something new that you came up with within the last 4 months due to your.
I wanted to show you that. Sure thing. Yes. Good catch. Okay, so
I'm interested in new stuff. So, because so far, I mean, you already had some justification for
yeah,
that
I didn't know that it was specifically 1/4 wavelength gravity wave, because this makes like this kind of like a quad wave sphere combination, and it helped me to understand some things. That's all. But sure, let's oh yeah, I made this from a photo my buddy took. It's pretty cool because see the ion tail and the bending off of the dust tail, nice, eh? But I digress.
So there are two tails to the
yeah, most comets. So this one is a straight line away from the sun. It's the ion tail.
Uh-huh.
And this one bends because it's getting constantly sucked down by gravity, and it's the dust tail. So this one is the ion tail. It moves with it. So as the comet, and so it moves like it continues to follow it and be straight. But this one always is falling away and dissipating.
Yeah, but it's not the Earth's gravity that's doing that, because Comet Neowise is like, I don't know, it's like far, far away still, right?
True. I guess this must be solar system gravity.
Yeah, it's kind of wondering whose gravity is that.
Yeah, it must be solar system.
And there's always been some question as to why that tail is always pointing away from, say, the sun. And I've not seen
the dust tail points to it.
No, the dust tail kind, but the ion tail is always pointing, I guess, away from the sun. Right? The loops around it always is pointing away from the sun. Though, if you were thinking about the tail, that particle is just coming off of the comet, you would think that that the tail should always be behind the motion of the comet, but it isn't. It's as if the comet tail is always getting blown away from the sun. Is how it
Yeah,
actually.
you're right.
Yeah.
I was wrong. So
Yeah, you've got that picture there. So there is some speculation as to, what exactly is going on here. Now I could, just speculate that, yeah, it's just a solar wind and it's blowing the comet. Although I do have some other more exotic explanations, which is that, I feel gravity is, say, a positive charge on the sun. And when the ions get blown off the comet, they're of course going to be repelled away from the sun. So that's my explanation for why the comet tail is
the
always
ion,
pointing away.
the ion always points exactly, but the dust tail points different ways.
Yeah, the dust tail points different ways. That's interesting. So they're at their maximum, pointing different directions when it's close to the sun.
I
But,
bet
they're very similar as they approach.
I bet that this is magnetic, and that's why it always points directly away. And this is getting blown by the sun. So as it comes across, it gets blown around. Maybe. I don't know that. That's just a guess.
Yeah, but that's interesting. I've not seen that the comet actually has two tails like that. Yeah, why do comets have tails? Why do they have two tails? That's I've never seen that before.
Yeah. I knew, but I didn't know about one being curvy and one being straight. I found that really cool.
Yeah, one being, you could really see that in that picture that you had there.
Yeah, that's from Roy Spencer. He's like a climate guy, but he's also an astrophysicist or something, and he takes a lot of astrophotography.
Yeah, so I can't really explain this second curved tail at all. Really, that's new data to me.
Yeah, me too. Definitely. Yeah, so there's
getting back to what's new in the last 4 months.
Yes, there's a wave quantum field.
So what's that?
I don't know. It wasn't what else. I don't know. It wasn't what I meant it to be. Exchange, interaction. I don't know. We could look at it if you want. We're kind of just freewheeling right now, right? Digressions are not unwelcome. So if we want to chase something, say, hey, let's chase that.
Oh yeah. It was just a science chat here, so. But that's just like, what happens when waves add together, right?
Yeah, it didn't look all that mind-blowing because it's not. But I don't know what it is exactly showing. You want to look at it more?
No, I think that was fairly straightforward. Not nearly as cool as the dual tail comet.
Yes. Something to do with wave function.
Yeah, is anyone else out here have any ideas as to where that second tail is coming from?
I don't know who else is with us today. Maybe it's only
we got Cornelius, we got Jim Marson, Dr. Lucas, Dynox. They're all giving us some comments here. Like Cornelius has a comment here, a comment on the comet, right? Okay. It says the ion tail is being driven electromagnetically driven away from the sun. The dust trail follows the curve of the path it has followed. Easily found information on the web. Okay, so.
Because primarily the dust tail primarily is gravitationally attracted back to itself. I remember that once the comet gets out of range of the sun, the tail actually goes back into the comet.
Well, it's like it doesn't have a. Yeah, it doesn't have a tail when it's very far away.
Right. the tail actually collapses back into the comet and freezes back into a ball, or a large percentage of it. Some of it gets lost because of the sun or cosmic wind or whatever. But
Well, I think that they're saying is that as it gets closer to the sun, it just gets hotter. So it's emitting particles, I think, is the mainstream thing here. So but Cornelius is saying that the dust trail is kind of doing what you think the trail should do, which is to be following behind the comet. Although
yes,
that picture that you showed, it still looked like it's still getting blown way the heck far away from the trajectory of the comet. So I don't think that that holds water, right? Because even the dust tail is still looking like it's very much pointing not in the direction of the comet, right?
yeah. I know in that orbit picture it like showed it being like even here, see, yeah, way off at times.
So this is one of those things that mainstream might tell you, but when you actually look at it, it's like, no, that's not right. Maybe it's kind of in the direction of the comet. It certainly seems that way.
Tail behind the anti-tail. Only when it.
See, Corey says the dust tail is like the smoke trail of a jet, not that complicated, except that the smoke trail of a jet directly follows behind the jet, as you would expect.
Yeah.
And if the comet were to do that, then it should just be right behind it should be pointing behind the comet at all times, and we don't see that. So that's kind of the big mystery here. So I don't know that we can just kind of dismiss that whole thing.
It does say here the ion tail made of gases always points along the streamlines of the solar wind because it's affected by the magnetic field of the plasma in the solar wind. So that's why it has the different angle and is always directly away, because it's getting pushed by and synchronized with the swirl of the wind, the solar wind. As it comes out, it has a swirl to it as well.
I mean, certainly that would be probably the most common explanation, that there's a solar wind. Solar wind, of course, always comes out away from the sun. And so that would be the expectation, that it's being blown away by the solar wind.
Because it does that.
Now, that's opposed to my crazy speculation, which is I think that the particles are actually being repelled from the sun. Would be they're not going along with the wind, but actually as they come off, they're actually running away from the sun.
Sure, yeah, I agree with you that the explanation that we're reading is not really what's happening, but in terms of like the observations are going to be correct, and but just like they're going to say, oh, well, it's pointing away because of this. And we know it's like the opposite. Well, it's like floating versus dropping and crap like that. We know they're wrong, but we can still like learn from their observations, right?
Yeah, the experimental results are experimental results, right?
Exactly. You only argue with the cause, not with the measured and observed effect. It's just the magic we want to get rid of. The claims of forces and force fields and crap like that. So yeah, anything we want to talk
about. One is mass is driven, the other is electromagnetically driven. It's like, okay, that's probably correct, but how is it that the mass is being driven? And why is it the ions are don't seem to be paying attention to things? Maybe because they're so much smaller. But yeah, it's a matter of speculation. I think there's still a lot of open questions on what's going on at the comet there.
See, there's a solar sheet depiction, and that's always swirling around the sun. It carries stuff with it. And that's the picture I was looking for, where I was saying a gravity wave showing head on. But that's actually a photon, not a gravity wave. Sorry. But I don't know why they're perceived as being different, except for maybe when it's mapped, maybe one is flat and one is popped out, and that's why they're showing looking the same, but they aren't. Like, see, if you took this and dropped it on the top of there, see how you get the same pattern, smaller, larger, like 1, 2, 3, 4 going alternating, 1, 2, 3, 4, and then it just repeats 1, 2, 3, 4, 1, 2, 3, 4.
Yeah, I mean, you could get that same kind of pattern if you're in a space shuttle and you had a globule of water or something just floating out in space, and you just tapped it, right? That would be another way to kind of get that same kind of shape.
Or if you have a gravitational field with a what do you call it? Membrane, or I don't know, is surface, like the surface of water. And then you have a wavetable that will create in 2D what will occur in 3D when it's not on the surface of something.
Yeah, it's kind of hard to do on Earth. That's why I suggest you do this in the space shuttle, where you can have a nice spherical globule of water, and the surface tension of water holds it together quite nicely. And then you could, you don't necessarily have to put a gravity wave into it. You could, blow on it or something, and put some force onto it, and then it would start vibrating.
Well, you can make it by like 2 interference patterns. I mean, like in a wavetable with 2, when you have those little balls, and the little ball drops in the water and creates a spherical wave, and when the 2 collide, it makes this as seen from the side. Easy peasy.
Yeah, it's an interference pattern. Yes.
Yes. But that's not what I wanted to show you. What I saw, the quarks.
Yeah, where's these quarks? I've never seen really a decent picture of a quark.
But this is now the guy in the video says this is not like supposed to represent their actual shapes, because they aren't ever an actual shape. This is a mathematical average of their core or something like that, of their weight.
Can you make that picture bigger?
Oh, absolutely. Yeah.
There we go.
So you see around each one of these triangles, each one of these peaks, you put a triangle, and then from triangle to triangle, 1, 2, 3, 4, and there's the sucking in. So these are like a cuboctahedron blowing through the triangle, sucking through the square. This is the opposite, because you can draw that. Oh, I did on the other one.
Well, the balloon tied together figures, that's kind of what they think like the S shells of electrons around atoms look like. Is that related? Because certainly
yes, exactly. Yes,
that's not
all is related. Everything is related.
Yeah, but I think that's a lot of hooey. So,
well, hooey to Yui.
Yeah, hooey to me. This was my opinion.
No, look, I got math on my side, dude. Yeah, I
have reality on mine. How about that?
Oh, you what?
Yeah, I have reality on mine. I have Lego bricks and things, and
okay. Well,
you could always fool yourself.
I have the standard model on my side.
Yeah, and that may turn out to be completely wrong. See, if the standard model is so smart, then how come they can't figure out what gravity is, right? If the standard model is so smart, how come they can't figure out what a magnetic field is, or even what a charge field is, or I don't know what any of these fields are, if they're so smart?
Because they started off with the wrong assumption. They started off believing that when a person walks into a wall, the person in the wall must exist and be solid. So they started with the assumption that what we see is what is solid.
Well, I think that's perfectly fine as a realist. It's like, yeah, I totally believe that. Yes, they're totally
what
solid.
we see is the frequencies bouncing off the surface of frequency-based collections within a defined area. So everything that you see when you look at a person, it's just frequencies that you're seeing.
Now,
the person-
I got that's a fundamental disagreement I have there.
yes,
And
it's like,
but-
yes, the person is there, because no, you can't, two people cannot walk through each other, because some collections of frequencies cannot walk through other collections of frequencies because they repel because of the nature of their frequencies.
But they don't do that, man. All frequencies, waves, they pass right through each other. That's
Right.
what
When there's
do.
no medium, they do, but we have a medium now, so they don't.
Yes, they do.
No,
Totally, every
not
single
when there's a medium, because the pilot wave reflects them back if they're discordant.
No, there can be cancellation of waves, but there is never a reflection. Never.
So anyway, I can paint one on here, or you guys can trust me. Around each of these 6 balloons, I can draw a square, and that will leave 8 triangles around these leaves. And that will create the corresponding blue-sized, purple-sized, and red-sized quarks. And one set of quarks is a cuboctahedron sucking in through the squares and out through the triangles. The other is the opposite. Out through the triangles, out through the squares, in through the triangles. So you got like this harmonic balance. They are like 2 halves of the same coin. But there's 3 sets of them: small, medium, and large. 6 flavors: small, medium, and large, with the in and the out. And then we're going to relate it back to this, because when you put those in a set, it's the best way to show it. There we go. Because when you spin these, you change the center to center lengths, unless you spin them all at exactly the same rate. And even then they're going to change, because when you spin 2 together, they have to lean left, like they have to do in order to rotate once, it has to go like, oops, sorry, I didn't mean to change the shape. That was an accident. In order to rotate once, it has to go like that because of its shape, because this ridge and this ridge are at different heights. So during the rotation, the ridges of the ones on the side of it will cause this to be happening. And that pattern will orbit, because first it has to be high in relation to that one, then in relation to that one, then into relation, etc. So it goes in like this sequence around. It's doing this as it goes, as it spins. Holy motorbike.
Yeah, motorbike, man.
Okay, so is that making sense to everybody? How this would have to go like this because of the ridges and because they're offset, because this one is lower than that one. Like they're like 2 sides of a ladder, but the 2 sides don't connect in the middle. So as it rotates, it's doing this, but it's also like going like, leaning into the screen and out of the screen as well. It's like doing one of those old-fashioned hokey movie UFO motions where it like wobbles as it rotates. And that, so because of it and because of these ridges, the whole thing is going to create a probability set where red is where ridge and ridge hit each other and made the center to center be the maximum, then you're going to get the biggest. And where they lined up perfectly, where red and blue just synchronized beautifully and they fit right in, you're going to get the smallest, and that's the blue. And then the in between is going to be a third one that's not shown, and it's going to be purple. And there's your three sizes of cuboctahedron based mathematics, where the red can only be going down, because from red is the maximum, so there's nothing more than red. Blue is the minimum, there's nothing less than blue. So blue is from there to the middle, red is from the largest to the middle, blue is from the smallest to the middle, and purple is the in between. So the part way towards the blue and part way towards the red is the purple in the middle. And that's how you get your three flavors of quarks with the two natures. See how all that makes sense?
So basically, you found your cuboctahedron, in this guy's work here, right? So you're relating that to.
Except again, dude says that his depiction is arbitrary, but again, something made him choose these, and these are not unfamiliar shapes. This, like you said, this is like straight out of the atomic orbital functions, right? So there's relation, and these are the heart of all baryonic matter in the universe, have a nature that for some reason people choose to show this way. Some qualified individuals, even though they said arbitrary. So that, to me, well, just the fact that what we are looking for as a neutron plus a proton, what we're looking for is something that causes 6 sets of 2 pairs of 3 types or 3 sizes. And this logically can cause this.
Well, certainly you have that shape certainly in common, right? That's
right. Now, also remember, we are looking for, why is there a 1 to 137th relationship?
Well, that actually, I mean, you mentioned that as being the ratio between the electron and the proton, but actually that ratio is like 1 to like 1,980 or something like that. The 1 over 137th is that's another special ratio, but it's not the mass of the electron to proton ratio. It's something else.
It's a fine structure constant. Fine structure constant.
Exactly. That's what it is. It has to do with the fine structure constant.
The inverse of it.
Okay, we're good. So what I'm going to suggest is that there could be a logical reason for that when you are working with HCP. So this stacking pattern is called HCP. If I say HCP, I mean 1 surrounded by 6 plus 3 above and 3 below. So 1 surrounded by 12. That's horizontal cubic packing or something like that. Horizontal close packing. And so this nature of it is when it's in rotation. And oh shit, I lost my track of where I was going with this. Something to do with cubic octahedrons. What were we looking at? Oh yeah, fine. Okay. So when you add 1, gets 12 around it, and then what comes next after that? The next set. But anyway, so then as you keep adding layers, you're going to hit the number 144. And then consider this relationship between the small and the large only emerges as the sets are in rotation. But as you make this bigger, it will be more defined, where red is more and more defined and blue is more and more defined, and the purple in the middle, it'll like kind of want to segregate into or coagulate is maybe a better word. The bigger, the more, So we're looking for what could cause 1 over 137. Well, we're expanding outwards from, going 1, 12, blah, blah, 144. But then what if you take one out? Because remember that each one is kind of like half there and half not there. And I said I would kind of explain that a little better.
Why are you looking for the inverse fine structure constant?
I thought it had to do with the mass of an electron to the mass of a proton.
Well, that's as Franklin just said, that would be about 1,836.
Yeah, and
The
that also
the fine structure constant has to do with the probability that a photon will interact with a charged particle, like an electron. It has nothing to do with nucleons that we're talking about here.
It will have some. See,
I mean, maybe that's just a new thing that maybe you didn't quite realize that James here is the expert on the fine structure constant. So
okay, no, that's good, because then maybe something will ring his bell that he'll see something and then he'll say, "Hey, Alistair, what about this?" And then that'll be cool too. So see how I'm
making an argument that
what I'd like to see, if I could ask a question, is what is the formula for this geometric object with the triangles and squares? What did you call that again?
That's a cuboctohedron.
Oh, okay. What is the formula for that? Because you're saying that God made the universe, and that I guess everywhere in the universe this formula is implemented. So you're going to have to explain how this formula is implemented. I mean, do you have supercomputers everywhere at every point in space, or exactly what? What is the formula for this cubocti?
Okay.
Whatever it is.
I never have suggested that God made anything. I suggest that those particles have always existed. Always. They are the fabric of existence, and they don't pop in or out. They're always there. Because that makes sense. That's logical. But sorry, close.
I mean, also, I don't know that. I mean, that's just a shape. I mean, it's like a cube has no formula. I mean, that's be like asking what's the formula for a cube, and it's like it has no formula. It's just a shape. It's a geometric.
Yes.
Well, you could consider it as a vector in an abstract space where the coordinates for each of these vertices in this geometrical object are listed. That's not exactly a formula, but it's certainly a mathematical definition of it.
Yes. Yeah, there are mathematics involved. Like there are density ratios depending on stacking patterns and center to center distances, and you can get different densities if you introduce a variety of sizes, but I don't play that game. So basically if you have perfect regular equal spheres, you get in their maximum density, you get one of two patterns, and the two patterns are density interchangeable, but one of them has 3 layers, A, B, and C, like this dealio, because the triangles will point different ways on the third layer. So yeah, so this is okay. So see, this layer, because it starts above, is a triangle down instead of a triangle up. It's not the same as this third layer. See, this goes ABA, this goes ABC. And so because of that, there are relationships between the distances between them. But it's like, okay, when they found that when they found that the double helix was a double helix, they did it not by, it didn't show up as a double helix. It showed up as a pattern that emerges if double helix are the underlying structure, because different underlying structures will create different patterns when they're seen from at larger scales. So when
You're talking about DNA helix?
when you look at it, yeah, you don't see any helixes. This is what you see. And that was the confirmation of the double helix structure, or sorry, this was what led them down the path to then model it using their balls and their sticks. And then they found a ball and stick pattern that made sense, the ACGT deal. It made sense, it made geometric sense, and it confirmed the mathematics of what they made matched back to this. They confirmed each other, and that was how the choice was made to conclude that DNA was double helix. So it's not always obvious. That doesn't say to like you, this doesn't say, oh, double helix, unless you know that it says double helix because you've studied it and know that it says double helixes. So it's different patterns will create different patterns. And close packing of spheres creates these patterns. These are like known emergent patterns, right? You stack a bunch of pool balls up. There's only two ways you can do it, in a pile of 3 or in a pile of 4. And when you stack them up this way, piles of 3 and 4 are both in there, just depending on which way you look at it.
Yeah, we got that. But what? And that's kind of just emergent out of the fact that your particles are spheres, right?
So yeah,
they couldn't hardly do anything else, right?
Okay, so but because they're wave based, they cause this.
The what do you call that? The
Cuboctahedron. Cuboctahedron, because it's made of 14 faces, but 8 of them are triangles, which means that the triangles have 24 equidistant surrounding edges. It's also got 6 squares, but squares have 4. So the squares have 6 times 4, 24 equidistant surrounding edges. So the 8 triangles and the 4 squares are sort of interchangeable. But when they're going like round and round and round, remember there's also some of this going on. So the red is like spherical. It like blends from being a cuboctahedron to being a sphere that's red around the outside. And the blue becomes a blue sphere, and the purple becomes a purple sphere in the middle. And so gravity is like the in and out towards the middle of this sphere. That is what causes gravity to exist. And the purple, instead of being a up and down, is like a clockwise, counterclockwise in between. The purple is like the top of the hurricane. It's like really, I don't know, maybe that's not the best way to put it. Like in the middle of a wave, in the middle, when the wave is like square waves, in the middle, there's going to be some calm and some turbulent, and some calm and some turbulent. Right? Like
so what does it have to do with how the world works? I'm kind of losing you there. It's more like kind of a geometry lesson than a physics lesson.
Okay.
Bring it back to what does that have to do with reality?
When you've got 12 surrounding 1, and you press equally exactly in the exact right spot against each 12, in the exact right spot, and then take the middle one out, it does not collapse. But if you were to point sideways on one, throw the whole thing into helter skelter and it collapses. Okay. So
Really? I mean, if you take anything out of that, it's going to collapse, isn't it?
Pardon?
You take any one of your balls out of that, I would say it's going to totally collapse.
Yes. No, that's not what. No, if you take the middle one out,
it would totally
collapses if there is an imbalance in the vector of pressure. If the vector of pressure is directly at from here to the center, like if it, what's going on?
So what does that have to do once again with
Okay, so
anything?
In a set of 12, it's 1 plus 12, but the center one is semi-disposable, especially where it's trapped in, like in here. If you take one out, is there going to be any change? Where are any going to go?
Perhaps another way to express Franklin's question concerning how this relates to physics. What is each of those balls there? Is that supposed to be a quark, or is it supposed to be a nucleon, or what?
It's the generator and host of a pilot wave field like this. These make this.
Each single ball in the middle here, at the bottom middle, you're showing a whole bunch of balls.
I mean, you've expressed it as being like a medium, like the thing that makes up the ether field.
Yes.
Yeah.
Yes.
So you can consider that it's a particle of the all-pervasive ether.
And within it, there is like this kind of reciprocal nature, which will coagulate and at different scales. So you'll get this kind of, like the magnet pattern will be an emergent pattern. See what I mean?
So what do you got there? What you pointing at?
It's like a magnetic field. Like imagine if this was the Earth and this green is the magnetic field with like a donut going through.
Yeah, can you make that a little bit bigger? You can barely see that, I guess.
Oh, sure, that you're right.
Yeah, there you go.
It's just showing, but that won't show up like this because it's like that would only happen if 12 were in isolation, but they're not. They're like this. So it's always like this kind of like handoff in 12 different directions. It's like it's getting a pressure from here, handing it to here, getting a pressure from here, handing it to here. So the one that's in here is like interchanging and exchanging in multiple vectors simultaneously because of the nature of its shape. So all of this is like a 12-dimensionally balanced mishmash of clockwise and counterclockwise pressures. But that's what I was trying to say before about, like, if you take one out, it sort of is inconsequential. But depending on its motions, it might be more consequential. Like if one is out of sync with its neighbors, it's going to cause more hits and pressures against its exterior while it's doing its rotation. So it's going to cause itself to seem to be bigger. So it'll be like, this means bigger, smaller, and in the middle. You see how that is like kind of what locks these together in a way? When you see the movie of these, it shows a ball kind of plopping out here. It goes bloop. It shows these in two sets of 3 triangles. And then it shows this ball being passed around, going bloop, bloop, bloop. And that's like this. And it's like,
I don't know that there'd be a big difference between your wavy ball and just, I don't know, like just a regular billiard ball. Regular spherical balls would generally do the same thing, would they not?
No. And I can state that with qualification. I mean, I'm a maybe close to professional level billiards player. No, not that's overstating it a bit. But I can hold my own. I've played against like the Canadian champion 9-ball player and won as many beers off him as he won off of me. Although I was having a good day and he probably wasn't trying his hardest. But he did for a couple of games. He definitely did, because after I beat him a couple of times, he got real serious. But so anyways, the moral of the story is I know to death how spheres interact when they're perfect regular. And I also know how they interact when they're not, because I also spent 7 years as a lawn bowler, and lawn bowls have biases. So when you look at one,
Yeah, lawn bowls have ridges on them, don't they?
not
Kind
ridges,
of like your particle.
not ridges, but you're close. They have a bias. Okay, so one side, see, it's shaved down a little bit. I mean, a lot, and the other side's only shaved down a little. I have 3 sets of these. One of them I won because I came in first in a big tournament. They worth about $250.
Really, these things aren't even spherical? How on earth do they manufacture that?
So yeah, well, I think they must shave them after they make them. My mom had a set that are antique. They're like wood, but mine are all like molded. So anyways, when you bowl it, depending on the speed, it will vary its amount of curvature. The faster it's going, the straighter it goes because it rides on the exact center. The slower it goes, it starts to lean over, and then it'll roll in and in and in, and sometimes it'll even curve and come back a little bit.
That reminds me a little bit about what Bob was saying earlier, in that like the deflection of an electron kind of varies depending upon its speed, and maybe it's due to this like bowling lawn bowling effect, where it's maybe, I don't know, not perfectly spherical or something.
Well, when you look at the deflections of the patterns that we're seeing in here,
Or maybe it
you
has
get
to
like
do
a
with the
sense of
deflection
like
of the comments.
radius and diameter and such. And then it was like the straight ones that were the Higgs because they had mass, so they traveled straight or something like that. But these curly ones are like all decaying. But these are like patterns that I didn't go to university for physics, but I lawn bowled for 7 years and watched the way those balls curled. And I alley bowled for about 10 years. And alley bowling is a whole other set of physics because alleys have oil on them to eliminate friction for the first 20 feet. And your ball has a different kind of lob to it because your ball is spherical, but where you drill the holes is a weight block. But if you're paying attention into what you're doing, you get the finger holes drilled off to one side of the weight block. So now the weight block is extra density to compensate for the lost mass of the finger holes. But you can take that lost mass and put it all the way on the side of the weight block. So now your weight block is like extra dense on one side, extra light on the other side, and those are both relative to the center of mass. So when you throw your ball down the lane, it slides at first, then it gets out of the oil and it starts to grip. Then you've delivered it with a twist or a hook or a curve, whatever you've done to that ball. But added to that is it's being sliding and storing up, like unifying the wobble with its spin while it's being traveling on the oil. And then it hits the friction part of the alley, and then you get hooks. And it's the offset weight block that allows you to maximize the hook. So when I talk about like the interactions between rotating spheres, and I say that a spherical based universe just will not work. And it's not without some significant attention to the nature of perfect regular spheres and non-perfect regular spheres that I am very happy and confident to say perfect regular spheres just don't work. Not as closest neighbor coupled units. If they're going to
yeah, that would be the trick, that they have to be, so close together that they're touching. But if they were in a gaseous state, then there would be no difference between the two if there was just gaseous state.
If they're gaseous, then they're not. But then how do they transfer torque?
Torque in which way? I mean, obviously, only
Clockwise and
solids can
counterclockwise.
transfer torques, right?
Like, how can they transfer clockwise and counterclockwise if they're not connected, touching?
Well, we have there are lots of forces that can be transmitted for things that are not touching, like sound waves. Obviously, transmit through non-touching air molecules, so that's not a problem.
Right. Okay. Sorry. I should backtrack a bit. I didn't mean to diss on your version of things, but what I'm saying is in mine, there's not also a medium in between them. There's not also a force field. There's not also a fluid. There's not also a charge or also a force. There's nothing. There's just those plus motion, period. And then this emerges. And then from this, and it's got this propensity within it. So then these emerge. And then the different elements emerge. Quanta emerge. And then from it's just because of divergent patterns, because of the density. Let's go back to the internet for a second. Because when you look at hexagonally close packed, there's a place where it says it real obviously.
Now, notice we have Cornelius and Eric have joined us on the live stream. So if you guys have any comments, go ahead and unmute and you can interact on the live stream.
Here we go. Look at highest density is known only in the case of 1, 2, 3, 8, and 24 dimensions. What that's trying to tell you is, like, if you were to kick it here, see, these two would want to split apart and let that one through. But if you were to kick this direction, your toe's going to hurt. You see the difference? If you kick that direction, it has a little bit of give. You kick this direction, zero give. Within a stack, okay, if you fill space with spheres, there are this many of those types of facets, I guess is one way of putting it. Does that make sense? You understand what I'm saying?
I'm not exactly sure what the relevance is.
Because
it's kind of a problem that if everything is a close packed sphere, then how do you distinguish things like, okay, there's a proton over here and there's an electron over there? If everything was so closely packed, there would not be any room for any such distinctions. Versus if you have like a gas, then it's like, yeah, then you can have an electron sitting over here, blank space, and then a proton sitting over there.
I'll answer that in a second. Where I was going with this is if you hear string theorists talk, what they'll tell you is that they want to suggest that the universe is 12-dimensional because 12-dimensional string theory makes the purest mathematical formula or something. It's the most beautiful, but it doesn't seem to work. So they had to downgrade and use 11 or 10 and 11 and 12. But they want to use 12, but they don't want to use 12 because it doesn't quite work. Well, this
personally, I don't think it stopped. I think it stops working after 3, but that's just me.
A cuboctahedral based universe is when it's in balance, it is 12 pressure channel balance points, I guess is the best way to put it. If you measure from here to here, it's the same as it is from the external to the center, right? So think of that as like a tuning fork. And there are 12 of those from the center, from the outside of a cuboctahedron to the center. There are 12 structure legs, I guess you call, I don't know, 12 center to centers going from the outside to the inside, and they match in length from center to center going parallel. See, like this would be a square cone. That
Yeah, but it seems to be just like a geometry lesson here. So once again, I'm trying to figure out, well, what exactly is new? Because we've discussed your things before.
New is the flavors and sizes and variation and types of quarks, and it all made sense. Like, I understand why these are as they are and why they relate so well to the periodic table and the standard model. I see
What
the
is the picture you're showing here? What is this picture?
That is alternate form of the periodic table. This is the periodic table just shown a different way.
So that's not representing like what an atom looks like or anything like that. That's just a different way to rearrange the periodic table.
This shows the relationship to the orbital shells. So this is the 2 orbital shell, the 8 orbital, the 18, the 32. This is the periodic table showing a different way as well. So you see it splits twice, then it splits 8 times, then so on. It's just showing like the fracture points.
So,
okay. Just different way of showing the rearranging the elements.
And
Alistair, if you go back to a couple of slides and you show your cuboctahedron, and also like in the lower right hand corner and upper left hand corner, do your spheres vary in size? Do they expand and contract to make?
No.
They don't.
So they are exactly what you would think of if you use the term solid, unibody, unchanging.
Okay, so in the midst of that field on the left, which permeates all of space, is that correct? That type of a field?
Yes.
In the midst of that field, how do I distinguish the cuboctahedron on the right within the middle of that?
Oh, because there would be like another layer on top and another layer below and then another layer on top and on top. It's just, I don't know how to graphically put myself into the middle of a pack of spheres.
Okay, but how do you distinguish when you have a pack of spheres and all the layers look like the layers we're looking at?
Right.
Okay, how does that cuboctahedron on the right, how does that cuboctahedron on the right get distinguished within that sphere?
That's what
this makes it look different.
So when you look at hexagonally based, which is like a combination between the 3 and 4 piles, then you get ABC, and this didn't show it where. It's like, it's about which direction the triangle points. So here,
yeah, but you're in the middle of a field of these things.
Yes.
And they're all the same size, and there's no space in between them, correct?
Correct.
So how does one grouping of them distinguish, how is one grouping of them distinguishable from another if there's not space in between them And if they're not different sizes, is it a difference in spin within them that changes then? Something that we can't see? If it's not physical size, then it must be the spin within them that's not visible to us.
Yeah, like there is not, like, if you were looking at this, and nowhere is there going to be like 13 that are acting independently as though they're just their own happy little cuboctahedron. It's just, this is the 1 to 12 nature, because every one of them, if it's not the outside of a cuboctahedron, it's the inside of the one around it. So the one in the middle here has 12 neighbors, but each one of these also have 12 neighbors.
So again, you're looking at the same thing. No matter which one I choose as the center, looking outwards, the environment looks exactly the same in all directions.
Right. Yes. Correct.
So
Yes.
if that's the case, looking inwards, the environment looks exactly the same throughout. And I have a field that there's nothing distinguishable about one part of it from the other. So how do you get an actual particle?
Yes, that's a great question. And if these were perfect regular spheres, that would be a game over. Your question would kill the whole point. But because this has a prime meridian, right?
Right.
Like the international date line.
All right. So it is exactly what I was saying. It's a difference in the spin, the angle of the spin, if nothing else.
Right. I could draw a 0 here, and that would be like midnight.
Okay. That clears up how you can distinguish one area from the other, because they're not all spinning in the same direction and along the same axis.
There's the two aspects to it.
So if you were to take the image above it and you were to rotate some of those ones that they all look like they have the same axis of spin there. If you were to take some of those and tilt their axis of spin, they would look different and unique than the rest of them. And now you have something that does look different and unique.
Right.
Okay, and that's what I'm asking. How do you make that? And you just answered that. It's not the size that changes; it's the rotational angle that changes.
The two things: the amount of rotation, and the orientation.
Amount. Okay.
The wobble, the lean, the precession and the recession.
Okay.
Like those cycles when the Earth goes around the sun.
Right.
You know how it precesses or something? The Milankovitch cycles.
But if they are if they are working against each other, then you also have to have a condition where if I were to flip one and totally upside down in the middle, that's not going to happen, because in order to have that happen, some of you have to progressively change the state of the ones around it, correct? Because if I just flip one upside down, it'll totally destroy the uniformity. If I don't flip, if it's just tilt the one slightly, then the ones around it have to tilt slightly in that direction, and there has to be a compensation of a little bit of a tilt at a time. It's kind of a wave function format, so that by the time you get to a dozen of them or so out, then you've got the image to the right, where some of them are tilted at the peaks in one direction, and some of them are tilted at the valleys in the other direction.
And so what you end up getting is quantum foam, is my guess, or my suggestion. Because they're always every single rotation, because it's got those 4 hemispheres, one is like projecting an expanding wave, one is projecting a collapsing wave, and then one of them is projecting a negative expanding wave, and one of them is projecting a negative collapsing wave. And those 4 things are always constantly the opposite and the reciprocal of one another. No matter what it does, it's always also undoing what it does.
Okay, when you're saying a collapsing wave and a negative collapsing wave, you're talking about the peaks and the troughs, or because I'm seeing, or the waves going towards the center and the waves going outwards from the center. and one being and a set of peaks going towards the center, and a set of peaks going away from the center, a set of peaks troughs going away from towards the center, and because I'm trying to figure out how you're talking about four waves.
Right.
Here.
So when you saw the overall image, it's a wave applied to it along this direction, this vector, right?
Mm-hmm.
So now see it as one. When I say expanding, I mean from the pole expanding down into becoming a 180-degree arc. And then again, going from a 180-degree arc, it comes down to being a single point. Meanwhile, on the other side, the opposite was happening here, and then the opposite of the mirror happens again. So you have the happening and the unhappening, and the mirror unhappening and the mirror happening. And they are the four quadrants that make that wave function that everybody likes to talk about.
Yeah.
Because
well, I think what you're doing is you're giving each segment of space the characteristic of an electromagnetic and gravitational field. So each one of these little spheres has within itself all those properties of electromagnetic and gravitation.
Yes, and so then when
correct?
you put them all together, they emerge from the collective.
All right. So you like many people are quantizing space into little incremental bits, and every bit of space has the same characteristic, and it's just basically a matter of how you turn that little bit of space.
Yes.
Yeah. Okay. So you're doing much like David Tome is doing, like Crit Franklin is doing, and even we got James some does that too. Each quanta, not qubit. What? I'm sorry.
Yeah, but did you have an argument against quantization? I mean, certainly that's right. That's totally quantized.
Well, I don't have any argument against quantization. I just quantize totally differently. The quantization that I utilize is a fundamental frequency, and it's harmonics basically. So you got a maximum frequency, and everything from there on out is a harmonic step of that frequency. So I quantize frequency and not necessarily individual space. This is a good way of representing the amount of energy in a particular area of space and the difference in it. But so it's more like the image on the right, where the waves exist, but the individual quantization doesn't have to, because the quantization is basically in the fundamental frequency and how long those waves are, because all the waves are at the same frequency. They're just traveling at different speeds. So it's totally different, and I really don't want to throw it in here at all. I'm just trying to understand Alistair's viewpoint.
And it's okay. I don't mind the introduction of a concept that could end up being complementary, because the way I figure it, there are a whole lot of right answers that are mathematically right, but like this is Bohmian mechanics,
right?
And I'm guessing that it's going to end up being found compatible with quantum foam mathematically. It's like, I don't say that Bohmian mechanics is wrong. I say is right, but I say this is the cause of
it. It's what Maxwell did as well, and like I said, what James is doing and what you're doing, you're basically quantizing locales of space, and what Franklin is doing. I mean, everybody's basically doing the same thing. So it makes for a solid mathematical model of how much energy might be in a particular area of space, and it's the difference in the amount of energy from one location to the other that makes the particles show up. I mean, your little spinning sphere is still a packet of waves that creates that spinning sphere.
Except they're a physical wave. This is a wave shape, not a. This isn't a wave. This is not a pliable. This is a billiard ball, wave shaped billiard ball. So that gives it a concreteness. There's no fudge factor. I can't say, well, this will just change shape as needed. No, I'm saying this is a shape, and you can take these shapes and calculate these and match them up to this and insert them into this and insert them into that, and you're going to find that all the way up it just matches.
Yeah, you're thinking it's like a hard billiard ball, right?
But within this billiard ball, you're saying there is no motion.
This is all singular density, no motion.
Okay, so because earlier you were saying as you got down lower into this, you get different troughs and peaks. As you went inside this billiard ball, there was a difference in blues and purples. You were showing, like on the right, you're showing now on the right is actually a combination of them.
Yeah.
So
Sorry, I was trying to highlight that there are the shapes, highlight the features of the shapes, which is, that this is a valley, but it's a valley with a different radius and a different depth, so a different amplitude, a different frequency. And they're all there in one. And it's when you make the set, and then from there, so you've got all those different features, but when you spin them, then they become purple, because it's like blue, red, blue, red, blue, red, you're going to get purple. Like it's the average, the in-between.
The difference that Cornelius is trying to drive at is that, your object there is an actual solid,
absolutely solid,
right?
Immutable.
The shape comes from a wave equation, can be calculated from, but it's not actually made out of waves.
Right. It's a wave particle dual manifestation. It's a wavicle that is actually not a wave at all. It's the duality without the duality. It is.
So those little.
Go ahead, James.
So those little balls in the bottom center picture of that cluster of balls, they're all the same size and they don't change size. So what is that size in meters? What is the radius of those little balls?
I don't know. Don't matter. Whatever size they are, we are the result. So if they were a mile across,
so you're saying that
would still exist, we would just be bigger.
The units of measurement in physics of mass, length, and time, we don't need to deal with those things in physics anymore, because it doesn't matter what size they are.
The Planck's constant aren't constants; they're self-feeding ratios. They relate the ratio of the frequency to the amplitude to the wavelength. This has that built right in. There is a wavelength and a frequency there, and there is a wavelength and a frequency there, and there.
Well, then what is the wavelength? You see, one of the problems that people have with quantization is that of the three basic units of measurement in physics, mass or energy, I like to think of it as energy, and length and time, when you just quantize one of those, like, for example, just quantizing the space parameter, you get into all kinds of problems. You need to quantize all three. In other words, you got to go full Monty, the full quantization, in order to get anywhere. When you quantize time, there is only one frequency, fundamental frequency, which is 1 over the quantized time, the inverse.
All right. So I'll explain for a sec. These are immutable. They don't change. It's like these are why we invented the word immutable. Because if you look at the word immutable, it specifically means does not change. How many things do you know of that don't change? In a universe that's 14 billion years old, something must have changed. So
it sounds like you're talking about a primary constant, Alistair. So when I ask you what the size of the little balls that are immutable and never change, you say it doesn't matter. To me, in my little world, that sounds to me like you're contradicting yourself.
No, what I'm saying is that their shape defines the ratios that are the foundation of the mathematics that we have created to describe the shape. I mean, the emergent mathematics. So we relate time to mass and energy, but we don't actually know what mass is. We end up with problems because we use self-recursive constants. So we are looking for a ratio between distance and frequency. And when you have a ratio between a distance and a frequency, that gives you time, because time is built right in there with the word frequency.
Frequency doesn't, this ball does not have frequency until it spins, until it changes in time. And it's the only change you've got, if it's a solid ball, is its rate of spin would be its frequency.
Okay, but follow me
Does that
here.
make sense? So is that rate of spin?
Okay,
is the time that James is looking for, I think.
Okay, follow me here for a second. If I roll around this surface with a rate of 1 RPM, I'm going to hear tat, 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 right there. But if I roll it this way, I'm going to hear nothing. That's a frequency of nothing. That's a frequency of what, 6, 12, whatever. You see?
Yeah, but how fast is tap 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 when I roll it, rotate in that direction? Because that is time. And you're saying but you also said earlier, I think the rate of spin on these things does change.
Yes.
Right?
Okay.
So you do have time, but you don't have quantized time necessarily.
No, you see, because I'm saying that this sets the ratio, it sets the nature of the ruler that we use. Because here is 1, here is 8, but they're like the same, but they're different paths. So that maybe that's not the best way to put it. Okay, you see here how these are they're all synchronized. They're all the prime meridians are all pointing the same direction. So now imagine maximum pressure is pointed from every direction, and none of them are spinning. And it's under like 1 billion tons of pressure. And you try to turn one, because turning one is going to force changes in the distance between this one and these two here. When I turn it, because of the pressure, there's huge resistance to turning it. So in mass,
that implies that they have mass. Then the inertial mass, each have inertial mass too.
They each have inertial mass because they have momentum. They have independent momentum, and they have imposed not imposed momentum. They have imposed push. Like,
so what is the inertial mass? In other words, with Cornelius's comments, which I find very welcome, it seems that no matter what you're saying, and by the way, I'm very, very sympathetic to the approach that Alistair is proposing. I mean, it's very, very imaginative, but we always get back to what is then the mass of each of these little balls in the center bottom row picture there. And then
right.
we're suddenly, and when we talk about the ratios of this, that, and the other, that's just another way of getting back to the units of measurement in physics of mass as a measure of energy content, length, and time.
Right.
And so that until you can tell me what is the unit of time, how many seconds, until you tell me what the length, the size of those little balls are, you're just flying, without a pilot.
Okay.
So,
This goes to the confirmation, right? If these things
time itself is quantized. It has got to have a reference. So it's basically the rate of spin of one of these compared to a rate of the spin of a reference one that gives you time. If one turns twice as fast as the other, then that gives you a tick of time. It says, and so you even to quantize time, you need a reference rate.
Okay. Yes, agreed. So
Exactly. And
So if
the
they're all
unit of
rotating,
measurement is seconds.
if they're all rotating at the same speed, then you have no time basically because they don't know it.
Right. They
They
don't
know it.
they don't all rotate at the same speed.
No, I
because-
understand that. I understand that.
because
I'm just saying a
existence is not
hypothetical.
existence is not uniform. Existence is based on things that like to orbit around each other in equal quantities. And so we're trying to set up a situation where we have something which, when it gets kicked out of balance, will segregate into two things that want to orbit around one another. Now, these are discrete, and they always exist. So time means nothing to them individually. However, they take up a volume of location, so they are occupying one of what we think might be a dimension called time, even though they are timeless. But they also, when they are considered relative to one another, they have motion which is relative, and that creates analog. So this is digital or discrete, quantized. This is analog over here. This is these, the distances, the little structure bars, stretching and contracting make this. And that's continuous. It is always, because these are all always pointing some direction. They never stop. They're always moving. And so
if I may just throw in a comment here, Alistair, you seem like a very brilliant guy. I would like, do you know anything about computer programming? I would suggest that you make a simulation of all of these things where you say, well, this moves and this contracts and this force going in. Make a computer simulation of this, and you're going to find that at some point you're going to have to define the units of measurement. What is the size of each little ball? Which I guess is, and what is the time? And if you make a computer simulation, you can actually show us what you're talking about.
Yeah.
Rather than just saying, oh, this pushes that, and this is opposite of that, and blah, blah, blah. You can just show us.
Okay.
With a computer simulation.
When I said that I don't know what the specific length is or the specific mass is, because they established the ratio. They established the 6 to the 1 to the 1 to the 12 to the distance between. They establish ratios between different things. So they will have a specific size. They will have a specific mass. But energy, because energy is how much spinning are they doing? So are they going to have a specific energy level? No, because they could be spinning 50 RPM. They could be spinning 5 billion. Well, no, they can't. There's not that much.
Okay, what I'm suggesting, if I may cut in here, my dear friend, is that if you had a computer simulation of this, it sounds like some phenomena in condensed matter physics, or AKA solid state physics. For example, the way atoms in metals arrange themselves in a pattern and so forth. There might be measurable things which your simulation can show, and this would then make it imperative that in order to match measured values in these solid state condensed matter objects, you would have to define a particular size for each of your little balls. Do you get the drift of what I'm saying? You could take your analysis one whole step further.
James, you're using a digital computer, James. So you have to define the clock rate of that digital computer. If the universe is an analog computer, you don't have a specific step. And so when you're talking about when you make a computer simulation, you have to define the time, yes, you do have to define the time increment, but you have to define the time increment because you're using a digital computer as a simulation tool. So you have to make it compatible with the tool you're using to simulate it, not because what you're simulating itself is digitized.
Excellent point. So Alistair could take his whole analysis a whole step further by that's why I asked, what's the formula for this cubic hexagon or whatever it is? To me, it's just a set of points, a vector in an abstract space, which is a set of points to define the vertices of this object. Whatever you define it as, when you start to simulate, you're going to be confronted with questions, as Cornelius pointed out, you're going to have to answer in order to get the job done. Then you could say, let's simulate, let's make a metal matrix, a matrix of metal atoms, and see where we have measurable values. This is going to force you to determine particular values for length and time that are uniquely compatible with your simulation and observed data in solid state physics.
Okay, so we're kind of getting towards the end of the 2 hours here.
Just one more second, and I just want to compliment Alistair. Alistair, did you do all these graphics and stuff that you did yourself, or?
Yeah.
Okay, I think you've done an excellent job there doing this, and I don't necessarily, I understand your viewpoint, and I don't necessarily go along with it, but I certainly understand the way you tried to simulate this, and I do appreciate the efforts you made in making the simulations. And I just wanted to say that before we ended the conference. So thank you.
Oh, thanks.
I second that motion.
When I say I made the graphics, like, for example, this ball I took from the magazine, or like, here I've taken parts of this and then made it into but I didn't like make that.
Okay.
But I've like cut and pasted a whack of stuff together like that I made from scratch, or oh, that's why, because it's like huge.
Okay, I was thinking your skills were much more farther advanced than I was thinking, but I think you still did an excellent job.
Like I made this part, I found and cut and paste that. I made some of this by layering stuff together.
Okay.
So some stuff I did, like, I've put the cuboctahedrons on, but the thing I grabbed out of a video, I do some stuff.
Okay, so these weren't actually generated by a computer running an equation. I guess that's what I was thinking possibly was happening. All right, thanks, Franklin, for taking the extra moment.
Yeah, they came from a video. The original picture came from a video, a Eugene something video. He's a really good guy, smart.
Yeah, but that's, the original research, that's why you only find it here at the Science Chat, right? So happy to give you an outlet. Happy to give you an outlet to explain your stuff. And but we are at the end of our 2 hours, so I just want to summarize a little bit. So we started out the hour with Bob Gray, and you guys really need to be coming out at 9 o'clock. I mean, on the hour sharp, right? We only had Bob there for a minute, but in any case, Bob was explaining that Weber Dynamics was explaining better explaining the results of actual experiments about electrons going past solenoids. So that was interesting. Or it's interesting that the Lorentz force law itself does not seem terribly accurate, right? And then we've had Alistair, and we got into his theory, and he had some recent discoveries. We looked at like the cuboctahedron. The shape seems to be appearing in other people's work with regards to quarks, and so we had a lot of discussion about how his theory works. It seemed like a lot of geometry to me, and I still have a kind of a hard time figuring out, what are the basics, how atoms and how light works and that kind of stuff. But it was always an interesting discussion. But I think that will do it for this episode of the Science Chat, and hopefully we'll see you next week.
Thanks. Cheers.